Hello students, in the previous video we had seen about LC oscillator which was used to generate sine wave signal. Here we are going to see about RC oscillators which is again used to generate sine wave signals. So these RC oscillators are classified into two types, RC phase shift oscillator and WEIN bridge oscillator. So the RC phase shift network is constructed as given. The same principle we use here an inverting amplifier which offers a 180-degree phase shift, and the output of here is taken and given to a RC network. You can compare that in an LC network you add a combination of inductances and capacitances, but here the output is given to an RC network. That too we are giving here as 3 RC networks. So why do we give here 3 RC networks? So if you take a simple RC network, you would have already seen that, or you would have already, it is very obvious that a single RC in this manner behaves like a high pass filter, and when you try to calculate the impedance of this particular RC network and you try to get an expression for this, you will be finding that this RC will offer a 90-degree phase shift, right? So I need a phase shift of total 180-degree in the feedback. So two such RCs are sufficient to get 180-degree phase shift. But in order to get if we use only two RCs, in that case the value of R will be very much small, which is impracticable. So what we do is, instead of taking two RC networks, we take three RC networks, and the value of R and C is chosen in such a manner that each RC network should give a phase shift of 60 degree. Hence, the total phase shift offered by these three RC networks will be equal to 180 degree, and hence the total phase shift offered by this oscillator is 360 degree, or it is equal to 0, satisfying the Barkhasan criteria. So this output, which is nothing but VF, which is taken and given back as input. So the analysis from this, we will be doing the analysis based on Barkhasan criteria. We will be deriving the expression for beta, and then we will be deriving the expression for frequency of oscillation. So let us determine the frequency of oscillation of this RC oscillator. Here we have considered the feedback part alone. So this is the output of the amplifier, which is given as input to the feedback network. So C, R, again C, R, and again CR. So 3 RC network, and output of this feedback network is VF, which is given as input to the amplifier. We know very well from the circuit of RC phase shift, the input resistance of the amplifier will be equal to R1. So all the analysis is done in terms of Laplace to make the simplification easier. So the reactances are given by, of capacitances are given by 1 by j omega c. So wherever we have j omega, it is replaced by s. So all capacitances have the reactance of 1 by sc. All the voltage nodes here are given as V1 of s, V2 of s, and Vf of s. So applying Kirchhoff's current law, I1 of s can be given as I2 of s plus I3 of s. So I1 of s can be written as V0 of s minus V1 of s divided by 1 by sc, which is equal to V1 of s divided by R, which is equal to V1 minus V2 divided by 1 by sc. So if you simplify, you can get an expression for V1 of s. Similarly, proceed on to the node V2. You can write it as I3 equal to I4 plus I5. So substituting for I3, V1 minus V2 divided by 1 by sc is equal to V2 by R is equal to V2 minus Vf divided by 1 by sc. So proceeding with this calculation and solving for V1, you will be getting an expression for V1 of S. From the previous two equations, you can arrive at this equation. Now, we are assuming that this resistance R1 is much greater than R. That is, the amplifier's input resistance R1 is going to be much greater. Obviously, only if this is greater, the bias current flowing into the amplifier will be equal to 0. That's why we are making R1 much greater than R. So when this bias current is equal to 0, I5 of S will be equal to I6 of S. So I5 of S will be equal to I6 of S, and hence you can find out the expression So how you can calculate Vf of s is Vf of s will be the voltage drop across this resistor R. So Vf of s is equal to R divided by R plus 1 by SC multiplied by the total applied voltage here. So the total applied voltage here is nothing but the previous node voltage, which is V2 of s. That's why we get this expression Vf of s is equal to R divided by R plus 1 by SC multiplied by V2 of s. Now we can write the expression of V2 of s is equal to RCS plus 1 divided by RCS into Vf of s. So substituting for this V2 of s in this particular equation, then we can derive the expression. Simplifying the expression for Vf of s divided by V0 of s, which is nothing but beta. So beta Vf by V0. If you simplify from the previous expression, you will be getting Vf by V0 in this manner. Similarly, the gain of an amplifier, that is the inverting amplifier, is given as V0 by Vf, which is nothing but minus Rf by R1, gain of an inverting amplifier. For the oscillator, we know that the necessary condition for the oscillator is A into beta equal to 1. So multiply A and the beta. So when you multiply, this will be equal to 1. So here we can substitute S is equal to j omega. So you substitute S is equal to j omega and cross multiply it toward the other side. So we will be getting this expression of minus Rf by R1 into minus j omega cube R cube C cube is equal to this entire expression will go to the other side. So we are getting here. Now our ultimate aim is we are going to equate the real and imaginary parts on both sides. So here in the left hand side the real part is 0. Whereas in the right hand side, what is the real part? Minus 6 omega squared R squared C squared plus 1. So automatically you can write minus 6 omega squared R squared C squared plus 1 is equal to 0. Similarly, you can equate the imaginary parts. So what are the imaginary part on the left hand side? Minus Rf divided by R1 into multiplied by minus. So it will be Rf divided by R1 into omega cube R cube C cube on the left hand side. In the right hand side, the imaginary part will be equal to, if you take j as common, you will be getting minus omega cube R cube C cube and then plus 5 omega RC, right? So we have to equate the real parts and imaginary parts. So equating the real parts as we discussed earlier, you will be getting this expression equal to 0. So obviously omega naught squared equal to 1 by 6 R squared C squared, and the frequency of oscillation F naught, if you substitute omega equal to 2 pi F naught. So F naught, you will simplify, you will be getting 1 by 2 pi square root of 6 into RC. Right? Similarly, when you equate the imaginary parts, equate the imaginary parts, you will be getting minus Rf by R1 is equal to 1 minus 5 omega naught squared R squared C squared. Here, in the place of omega naught squared, you substitute 1 by 6 R squared C squared. So, and when you take the modulus of this value, you will be getting Rf by R1 is equal to 29, or you have to choose the value of Rf is equal to 29 R1, that is the gain of the amplifier A should be equal to 29. So the gain of the amplifier should be at least 29, right? And the total phase shift around the loop should be exactly 360 degree. So when these conditions are met, this RC phase shift oscillator will oscillate at a frequency of F naught equal to 1 by 2 pi into square root of 6 RC, and it will also give sustained oscillations. So these RC oscillators are classified into two types: RC phase shift oscillator and WEIN bridge oscillator. So considering the feedback part alone, which is the output of the amplifier is V0. It is given to the series RC network, and then you have a parallel RC network. Between the series and parallel RC network, you will be taking your output VF. So we have seen that the total phase shift around this should be equal to 0 or 360 for the oscillations to occur. So this will occur only when the bridge is balanced at the resonance. Hence, the frequency of oscillation is the resonant frequency of the balanced bridge. So here, to determine the frequency of oscillation, it is very obvious that V of S is nothing but voltage across this parallel RC. So R and the capacitance is 1 by SC. So net impedance is ZP of S, parallel of S. So VF of S can be written as ZP of S divided by ZP of S plus R. ZP of S divided by ZP of S plus ZS of S into the total applied voltage V0 of S, where ZP is nothing but parallel combination of these two. So R parallel with 1 by SC, which can be simplified like this. And similarly, ZS of S is series combination of R and 1C, which can be further simplified like this. We can write the value of beta. So beta is nothing but output of the feedback network VF divided by the input of the feedback network V0. So which can be further written as, you can substitute the value of VF over here. So V0 and V0 will be getting cancelled. You will be evaluating here. Substitute the values of ZP and ZS. You will be getting an expression like this, right? So this is the expression for beta. Then as I already told, the amplifier A was nothing but a non-inverting amplifier, and the gain of the non-inverting amplifier is given as A equal to V0 divided by V1 Vi, or V0 which is given by 1 plus Rf divided by R1, right? So for satisfying the condition of oscillation, this A beta modulus should be equal to 1. So multiply this A by this beta. So multiply this A by this beta, and as we did in the previous case, you have to substitute the value of S is equal to j omega and bring it to the two other sides, and then equate the real part and imaginary parts. Hence, substituting S is equal to j omega naught, we are getting 1 plus Rf into j omega naught Rc. Taking it to the denominator to the other side, you will be getting an expression. So here, while equating the real parts, you see that on left hand side there is no real part. So 1 minus omega naught squared R squared C squared equal to 1. On simplifying, you will be getting the frequency of oscillation F0 equal to 1 by 2 pi RC. So the frequency of oscillation of a Wien bridge oscillator is F0 equal to 1 by 2 pi RC. Similarly, when you equate the imaginary parts, you will be getting 1 plus Rf by R1 j omega naught Rc. So j omega naught can get cancelled, right? So automatically you will be getting AV is equal to 1 plus Rf by R1. This 1 plus Rf by R1 will be equal to 3. So which is nothing but gain of the amplifier AV. So which is equal to Rf is equal to 2 times of R1. So when you choose the value of Rf is equal to 2 types of R1, you will be getting the amplifier gain as 3. So maintaining the amplifier gain as 3 will ensure that the Wien bridge oscillator will produce sustained oscillations. So Wien bridge oscillator is ideal in low frequency applications like audio generators. It is not suitable for high frequency applications because phase shift through the amplifier and phase shift of lead lag circuit jointly cause resonance. But in contrast, in LC oscillators, they are actually used for high frequency applications. Thank you, students.